Hello, welcome to my class. Today I'm going to cover Laplace transforms for system of linear differential equations. Let me start the class right away. First, a motivations discussion. We can rewrite a second order linear differential equation as a system of two first order linear differential equations. For example, consider an initial value problem of second order ay double prime plus by prime plus cy equals to ft with initial conditions y0 equals to k0, y prime 0 equals to k1. Next, let's introduce our variables. x1 equals to y and x2 equals to y primes. Then this given initial value problem reduces to x1 prime equals to x2, which is here, and x2 prime is y double prime, and the y double prime equals to, from this given initial value problem, solve for y double prime, divide by a, take this by prime plus cy to the right side. So y double prime equals to 1 over a times ft minus bx2 minus cx1, and initial conditions x1 0 is k0 and x2 0 is k1. So that means we reduce the second order linear differential equation as a system. Now it's a 2 by 2 system of two first order linear differential equations. Okay, so now let me recall from section 8.2, we can express a system of linear equation as a single matrix form. For example, example 0, let me scroll down. Write the following system of differential equations in a matrix form. So it's a differential equation, another differential equations, but for us, we stick on homogeneous system. So put f1t and f2t both 0. Then for the homogeneous case, we have a differential equations here. X prime equals to x plus 2y, y prime equals to 3x plus 4y. Let me scroll down. Then rearrange this system into a matrix form. So we write x prime, y prime in one column, 1, 2, 3, 4 in another matrix, and xy in another matrix. So then this is of the form x prime equals to ax, or ax equals to b form. So in this lecture, we will analyze the system of linear differential equations using Laplace transforms. So let me scroll down. So then at this time, we can ask questions to ourselves: how to solve a system of linear equations of the form ax equals to b using Laplace transforms. Let me give you the steps to remember. So the idea is to solve differential equations, system of differential equations using Laplace transforms methods. First step, take a Laplace transform of each differential equations. Step 2, get a matrix form. Now this capital X is a transform, or this is a Laplace transform of little x. Ax equals to b, where A is a coefficient matrix, and solve for capital X, which is this form here. We need to compute the inverse of our coefficient matrix and multiply through this b. And to compute the inverse, here's a formula for matrix A equals to A, B, C, D. The inverse is 1 over determinant of A, and this is the matrix come from the matrix A. So here this diagonally we switch the positions, and this diagonally we switch the sign. So this is coming from our coefficient matrix A. And now we have a solution in the frequency domain. Now we use the inverse Laplace transform. This is step number 4. Take inverse Laplace transform to recover the solution in the time domain, which will be the solution of given system of differential equations. Great. Now let's implement those ideas and to solve the following equations or following system. Let me scroll down. So the example 1, solve a system of initial value problem. X prime equals to 2x plus y prime equals to 3x plus 4y. Initial conditions are x0 1, y0 0. So the first step, let's begin. Take Laplace transform of each differential equations. So the Laplace transform of x prime is this left hand side, and Laplace transform of 2x plus y is this right hand side. Similarly, the Laplace transform of y prime equals to 3x plus 4y is given here. And in the next step, put the initial conditions. X0 is 1, y0 is 0. And now let's rearrange the term here. So bring all the capital X and capital Y in one hand side and the constant to the other hand side. So this is the rearrangement here. So s minus 2 of capital X minus capital Y equals to, take this 1 to the right side, 1. Similarly, this is the negative 3 capital X minus, this is the s minus 4 here. So I think we should have, this is a plus, this is a plus, here's a typo, this is a plus, capital Y is equals to, take this 0 to the right side. Now we have a system of two equations. Now we can rewrite this system in a matrix form. So it's a matrix form here. We collect the coefficient matrix, the coefficient here, and then the capital X, capital Y, another matrix, and this is the constant on the right side, which is another matrix, 1, 0. And then next, we need to solve for capital X and capital Y. First find the inverse of this coefficient matrix. So for that, first compute the determinant. Your determinant we multiply this diagonally, and then minus we multiply this diagonally, which turns out to be a quadratic in variable s. And we factor, we have these two factors. Then capital X, capital Y equals to 1 over the determinant. And on the matrix here, we switch the positions from this coefficient matrix here. S minus 4 goes here, s minus 2 goes here. And on this diagonally, we switch the sign. Minus 3 becomes plus 3, minus 1 becomes plus 1. And we multiply through this 1, 0, 1, 0. In the next step, write down this 1 over s minus 5 times s minus 1 as it is. Multiply this 2 matrix. We multiply matrix, first multiply horizontally and multiply vertically and add these two results. So s minus 4 times 1 plus 1 times 0, 0. So simply s minus 4. Similarly, 3 times 1 plus s minus 2 times 0, which is 0. So simply 3. Let me scroll down. So now we found the solution for capital X and capital Y. So capital X equals to s minus 4 over this factor, and capital Y equals to 3 over this factor, which is s minus 5 times s minus 1. Great. So now let's solve for each of these x and the capital X and capital Y. Then capital X equals to, that I said, s minus 4 over s minus 5 times s minus 1. So use partial fractions to decompose these fractions, or write this fraction into a sum or difference of two simpler fractions. So both of these factors are linear in our denominator. So we introduce constant a over one factor plus constant b over another factor. So next we're going to compute the value of a and b. Then it turned out to be a is 1/4, b is 3/4. Finally, take inverse Laplace transform to find the solution in time domain. So little xt to the left side equals to 1/4 as it is, inverse Laplace transform of 1 over s minus 5 is simply e to the 5t plus 3/4 as it is inverse Laplace transform of 1 over s minus 1 equals to e to the t. So we got e to the xt equals to this expression. Now similarly, let's solve for capital Y and take inverse Laplace transform of capital Y and get little yt. So capital Y of s equals to 3 over same denominator, use partial fractions where a and b are constant. Then a turns out to be 3/4, b turns out to be negative 3/4. Then use, let me scroll down, then take inverse Laplace transform using Laplace transform table. So little yt equals to 3/4 e to the 5t minus 3/4 e to the t. Now we got the solution at little xt, little yt of given initial value problem. It means system of differential equations. Great. Now let's move on. And now let's talk about coupled spring models, which consist of 2 springs and 2 weights. Let me put this to here. That's better. Yeah. Oh, this one. So suppose two springs are attached together here. This is the ceiling. I'm explaining on the first diagram. And the spring A has constant K1, and at the lower end of the first spring, or spring A, the weight of mass M1 is attached. And on the bottom of that weight, another spring B is attached, and at the lower end of the spring B, M2, weight M2 is attached. The K2 is the spring constant of spring B, K1 is a constant for spring A, and the equilibrium positions, so here is no displacement, x1 is 0, x2 is 0. And now in the second diagram, let me scroll this up here. In the second diagram, we put the motion. Then this M1 and M2 both elongates, or they displace here. I mean displacement is for M1, the x1 is the displacement. For M2, x2 is the displacement. So in the third diagrams, let's talk about the forces acting on the masses. Oh, by the way, the downward direction is the positive directions. So to the first mass, M1, the forces, 2 forces acting, one force is acting upwards, one force is acting downwards, and x2 minus x1 is the net elongation or net displacement. Okay, so for M1, K1 x1, K1 is the spring constant of spring A, and K1 x1, and the downward force is K2 times the net displacement. But for second mass, only one force is acting, which is acting upwards only, so which is negative K2 times the net displacement. Okay, so now let's move on. So now by using Newton's second law, we will have these equations. So now these equations, these are the net, sum of the forces for the first mass, and this is the sum of the forces acting on the second mass. So the Newton's second law gives us this. It's a system now, system of equations. Hence we have a pair of second order linear differential equations. Now next talk about how to solve these systems. Now let's make the following assumptions. So let's pick M1 is 1, M2 is 1, the K1 is 6, K2 is 4, x1 0, the initial condition is 0, x1 prime 0 is 1, x2 0 is 0, x2 prime 0 is negative 1. So this means that we have this system now. So I'm just replacing m1 by 1. So x1 double prime equals to, so it's a negative k1 plus k2, 6 plus 4, which is 10, x1 plus k2 is 4, 4x2. Similarly, m2 is 1, so x2 double prime equals to k2 is 4, x1 minus k2 is 4, x2, and the initial conditions are the same as here. So now let's solve a system. I'm picking those values just in particular. Okay, in particular, I'm showing you the coupled spring models gives us a system of, or the pair of second order linear differential equations, and now we are solving by picking those values here. Let me scroll down. That's better. So then our first step, or we begin by taking the Laplace transform of each of the differential equations. Oh, here the differential equations here. So then take Laplace transform of this first one here. So x1 double prime becomes s square x1. This is the Laplace transform of little x1, and then use the formula. And also I skip here by using the initial conditions because my initial conditions is a 0 here. So this is actually s square capital X1 minus s times little x1 minus little x1 prime. So the middle term, s times little x1, which is 0, gives us 0, and little x1 prime at 0 gives me this 1. So that's why I put this value here. Similarly, take Laplace transform of the second differential equation, which turns out to be this one after you substituted the initial conditions, and rewrite this system in a matrix form. So this is the next step. So this is the coefficients, and this is x1, x2. These are the capital X1 s, capital X2 s. These are the transforms. Right side is constant 1. This becomes minus 1. Great. So let's move on. So next we're going to find the inverse of this coefficients matrix and multiply through this 1 and minus 1, this matrix. So we compute the determinant here, which gives us s square plus 2 times s square plus 12. So capital X1, capital X2 equals to 1 over the determinant times the matrix. And this matrix we got from this coefficient matrix. This diagonally we switch the positions, this diagonally we switch the sign, times multiply through 1 minus 1 matrix. So the next step, we copy down this one here. Now we multiply these two matrix. We multiply horizontally and vertically and add them, which gives us s square minus s square plus 6. So then we have capital X1 equals to s square over this denominator, s square plus 2 times s square plus 12. Similarly, capital X2 equals to negative s square plus 6 over s square plus 2 times s square plus 12. First, let's work on capital X1. So capital X1 equals to s square over s square plus 2 times s square plus 12. Use partial fractions to write this fraction as a sum of simpler fractions. So here both of the factors are quadratic. You need to introduce the linear factor on the top. Then solve it. Then we will have these forms here. Capital X1 equals to negative 1/5 over s square plus 2 plus 6/5 over s square plus 12. Let me scroll down. Then take an inverse Laplace transform to get the little x1. So little x1 equals to negative 1/5 constant as it is. So to compute the inverse Laplace transform of 1 over s squared plus 2, we have to manipulate, multiply by radical 2, divide by radical 2. For the second one, we do the same. First, manipulate here, or the modify, by multiplying by radical 12, dividing by radical 12. Then the last line here, little x1 equals to negative 1 over this 5 times radical 2. Inverse Laplace transform of radical 2 over s squared plus 2 is simply sine radical 2t plus 6 over 5 times radical 12. Then inverse, oh, this is not Laplace transform, this is the type here, this is the inverse Laplace transform. So the inverse Laplace transform of radical 12 over s squared plus radical 12 e square, which is 12, is sine radical 12t. Great. Now let's move on. Now similarly, for capital X2 equals to negative times s squared plus 6 over s squared plus 2 times s squared plus 12, use partial fractions. We got the constant negative 2/5 over the first factor minus 3/5 over the second factor. Similarly, we need to modify here. We need to multiply by radical 2, divide by radical 2. Here, multiply by radical 12, divide by radical 12, just like here. Then our final answer is by taking inverse Laplace transform, little x2 equals to negative 2/5 times 1 over radical 2 times sine radical 2t minus 3/5 times 1 over radical 12 times sine radical 12t. Great. Now let's move on. Let's do example 3. So solve this differential equation system. So x prime equals to x minus y, y prime equals to 9x plus 7y, given initial conditions. X0 is 2, y0 is negative 6. It's a repeated root case. So the idea, let's begin by taking Laplace transform of each of the differential equations. So the Laplace transform of little x prime is s times capital X minus the x0, which is 2. I put the initial conditions here, and the Laplace transform little x minus little y becomes capital X minus capital Y. Similarly, take a Laplace transform of second differential equations, and then rearrange the term, write in the matrix form, then find the inverse of this quotient matrix to solve for capital X and capital Y. So we first find the determinant here. So determinant gives us s minus 4 squared, so that would means the repeated case. Then solve for capital X, capital Y. So 1 over determinant, that means we are computing the inverse of this coefficient matrix. So then here on this diagonally we switch the positions, this diagonally we switch the sign, and multiply through this 2, 6. The next step, I'm just following the routine computation here. 1 over s minus 4 outside square. Then multiply these two matrix, multiply horizontally, multiply vertically, and add them. So s minus, for example, s minus 7 times 2 minus 1 times 6. This is the 2s minus 20. But this second terms here, this is multiply 9 times 2 plus 6 times s minus 1, and simplify gives you 6s plus 12. And now we got capital X equals to 2s minus 20 over this denominator, s minus 4 outside square. Capital Y equals to 6s plus 12 over same denominator, s minus 4 outside square. So let's solve for capital X first. So capital X equals to 2s minus 20 over s minus 4 square. So now here is the shift is 4 down here, but there is no shift on my numerator, so we have to force the shift on the numerator first. So let's put the shift. 2 times s minus 4 plus 4 minus 20 over same denominator. Then make a group s minus 4 one group, 4 another group. Multiply by this 2, so 2 times s minus 4 plus 2 times 4 is 8. So in the next one, write down 2 times s minus 4 over s minus 4 is square, so cancel 1 s minus 4, which gives you 2 over s minus 4. And then next here, so multiply this constant and simplify. 2 times 4 is 8. 8 minus 12 is, sorry, 8 minus 20 is negative 12 over s minus 4 square. Then take inverse Laplace transform. So capital X becomes little x equals to 2. Inverse Laplace transform of 1 over s minus 4 is e to the 40 minus 12. The inverse Laplace transform of 1 over s minus 4 outside square is little t times e to the power 4t. I use formula number 17 in our Laplace transform table. Great. Let's move on. Now capital Y equals to, from here, 6s plus 12 over s minus 4 outside square. Same as before, put the shift. So shift is now negative 4 plus 4. And the next one, 6 times s minus 4 over s minus 4 is square. So cancel 1 s minus 4. That gives you 6 over simply s minus 4. And this constant comes from this here. 6 times 4 is 24. 24 minus 12 is minus. Oh, this is plus here. Oh, no, that's another typo here. So 6 times 4 is plus 24, minus 12 is plus 12, not minus 12. So let me hide it. That means that's a plus. Plus 12 over s minus 4 is square. So then take inverse Laplace transform. So capital Y inverse Laplace transform of capital Y is little y equals to 6 times inverse Laplace transform of 1 over s minus 4 is e to the 40. It's now plus 12. Then inverse Laplace transform of 1 over s minus 4 outside square is simply t times e to the 2t. Great. Let's move on. Let's do another types one with the same types of computations. So complete the square types. So let's do example 4. Solve the system of differential equations using Laplace transforms. Given differential equations system is little x prime equals to 5, x minus 4y, y prime equals to 2x plus y. These are the initial conditions. With x is 3, y0 is negative 4. As before, begin taking Laplace transform of each of these differential equations using the formula and use initial conditions, and then write this system in a matrix form. Now we have a matrix form here. So please pause this video and work out here. Then next, now I need to solve for capital X and capital Y. First find the inverse of this coefficient matrix. To find the inverse, find the determinant of this coefficient matrix and then write down the matrix inverse equals to 1 over the determinant times another matrix. That matrix is just obtained by switching this diagonally and switching sign this diagonally and multiply through 3, negative 4. Great. So first compute the determinant, which gives you here. So that is the computing this square is here. So s minus 3 outside is square plus 4. Then our, oh, maybe what is better? Maybe that's better. That's better. So then capital X, capital Y, which is the matrix, equals to 1 over determinant, which is s minus 3 outside is square plus 4. Then times the another matrix. That matrix comes from this coefficient matrix by switching this diagonally positions and this diagonally switching sign. Multiply through another matrix 3, negative 4, which is on the right side. Awesome. Let me scroll down and then write down this, the first this terms, which is 1 over s minus 3 outside is square plus 4, and multiply these two matrices. Again, multiply horizontally, multiply vertically, add them, which gives us this one. Then now we found capital X equals to 3s plus 13 over s minus 3 quantity square plus 4. Capital Y equals to negative 4s plus 26 over s minus 3 outside is square plus 4. Great. So here, so capital X equals to 3s plus 13 from here over s minus 3 square plus 4. Now put the shift on numerator. Shift is 3 here, so s minus 3 plus 13 over the same denominator. Then in the next line here, so multiply this 3. So 3, make one group s minus 3 over the same denominator, plus 3 times 3 is 9, 9 plus 13 is 22 over the same denominator. And then let's compute the inverse. So here first unshift, which is 3s over s square plus 4. Find the inverse Laplace transform of 3s over s square plus 4, which is 3 cosine 2t. Then there is a shift, so we have to modify this little ft by multiplying e to the power negative 3t. Similarly, in the second terms, write the unshifted form, which is 22 over s square plus 4. We need to modify, so modify by multiplying by 2, and then this constant is 11 times 22, so the constant is 11. Then the inverse Laplace transform of 2 over s square plus 4 is simply sine 2t, and modify by multiplying e to the power negative 3t. So our final answer is little xt equals to 3 times cosine 2t times e to the power negative 3t. This is the term here. Then the second is plus 11 times sine 2t times e to the power negative 3t. Awesome. I hope this little computations make sense to you all. Similarly, let's move on. Scroll down here. Oh, we're almost there. Great. So now capital Y equals to negative 4s plus 26 over s minus 3 outside is square plus 4. Now, same as before, put the shift on our numerator. So negative 4 times s minus 3 plus 3, same denominator, plus 26, and make a group here, s minus 3 one group, 3 another group. So negative 4 times s minus 3 over the denominator, s minus 3 outside is square plus 4, and plus the negative 4 times 3 is negative 12, negative 12 plus 26 is positive 14, 14 over same denominator, s minus 3 square plus 4. In the second one, we need to modify by dividing by 2 and multiplying by 2, and then apply the formula. So then this is kind of same as here. So first unshift is, so to find the inverse here, first unshift, which is negative 4s over s square plus 4, and then which gives you negative 4 times cosine 2t, and modify by multiplying e to the power negative 3t. So this is the first term. Now plus 2, 7 times 14, so 7 there, and inverse Laplace transform of 2 over s square plus 4 is sine 2t, and modify sine 2t by multiplying e to the power negative 3t. So the final is 7 times e to the negative 3t times sine 2t. So great. So we finished this system of linear differential equations for Laplace transforms. Thank you.